When alkenes are treated with dilute sulfuric acid, they undergo electrophilic addition of water to produce alcohols. The reaction will go through carbocation intermediates, with tertiary being favored over secondary when unsymmetrical alkenes are employed. This will then lead to mixtures of regioisomeric alcohol products. The overall pathway to the alcohols is reversible, however the products are favored at lower temperatures and in dilute acid. The alkene goes after the acid in the rate-determining proton transfer step to generate carbocation intermediates. Water solvent then traps the carbocations to give oxonium ions, which are then deprotonated by solvent to give the alcohols. In the first step of the reaction, the acid catalyst is consumed, and in the last step it is regenerated. The first step, the formation of the carbocation, is rate-determining. Here, proton transfer may occur at either carbon and at either face of the alkene to produce the 6-electron tertiary and secondary carbocations. The tertiary pathway will be preferred due to significant electron donation from the 9 adjacent beta bonds in the form of hyperconjugation. This selectivity is referred to as Markov-Nikov addition, in which the major product will arise via the more stabilized carbocation intermediate. The second step in this pathway is a fast trapping of the planar carbocations by water from the solvent to give the 8-electron saturated oxonium intermediates. In the case of the tertiary cation, which is not prochiral, attack occurs to give a single tertiary oxonium ion that is symmetrical and not chiral. To complete the formation of the tertiary alcohol product, a molecule of water solvent acts as a base and removes one of the acidic protons from the tertiary oxonium ion in a fast proton transfer step. Since addition of proton to the alkene in the first step also gave a prochiral secondary carbocation, those intermediates are attacked by water, which results in a mixture of 2 stereoisomers. The nucleophile donates into either side of the p orbital that constitutes the positive charge, thus resulting in both enantiomeric outcomes. This will mean that a racemic mixture of secondary oxonium ions will result. Fast transfer of a proton from the secondary oxonium ions to the water solvent will then complete the formation of the racemic mixture of secondary alcohols. Overall, the reaction of aqueous sulfuric acid with alkenes is known to go through carbocation intermediates to give alcohols. When the starting material is unsymmetrical, regioselective addition is observed, with the major product arising through the more stabilized intermediate. Stereochemical issues arise in the products if the alkene and intermediate have the potential to be flat and prochiral. Here the major isomer is symmetrical and not chiral, while the minor regioisomer is a racemic mixture of chiral alcohols.